Kevin Coffey, who talked about his temporal structure curved in Newtonian Gravitation Theory.
Okay, so thank you very much. Pleasure to be here.
All right, Kevin, you have to push once. Just once.
Just once.
Yeah.
Great. Okay, so thank you. It's a pleasure to be here. The question I want to think about in this talk is the status of inertial structure and the gravitational field in Newtonian gravitation. So I want to start by laying out two different views. One is what we might call the old received view, which is the view that you would have of Newtonian gravitation if you picked up an ordinary textbook on the material. And the idea is just that matter exerts gravitational forces on other matter, and that's transmitted by intervening fields that mediate the dynamical interactions. And here's a very childish diagram to help illustrate this. If you're familiar with some of the physics, you'll know that there are various things that are misleading about this diagram. I'll try to highlight a few of those along the way. But because some of this talk is going to be mathematical in nature, I want to have a couple diagrams to sort of draw out the sort of heuristic view that I'm getting. So the idea is just that we have inertial trajectories and gravitational field generated by matter, and objects are deflected from those inertial trajectories by the gravitational field. And of course, this view requires a space-time that has an inertial structure that distinguishes free particles from those of gravitationally accelerated views. And of course, we can distinguish this view, what I'm calling the old received view, with the view that I'm calling the new received view. The new received view is the idea that Newtonian gravitation is best understood as a theory of curved space-time without any gravitational field. And so here's another sort of picture where the idea is that the inertial structure has been bent and that or curved, and that there's no gravitational field in the diagram. And the idea is that the presence of matter curves the geometry of space-time such that objects are following the straightest trajectories or geodesics within that space-time, and they follow the same trajectories as they would have on the old view, except now there's no gravitational field deflecting. And for those that don't follow this literature, it may be a little bit surprising to realize that this has become, I think, the new orthodoxy amongst people studying Newtonian gravitation theory. And in all this view, the distinction between inertial structure and gravitational field is often claimed to be unphysical or gauged or conventional. So here's Eleanor Knox writing in 2014. She writes, curved spacetime is a formulation that captures the best spacetime setting for Newtonian gravitation judged by its own lights. This should lead us to interpret both the gravitational field and the connection as gauged quantities, that is conventional or not directly representing physical quantities. And this view has been endorsed by a variety of philosophers of physics, Michael Friedman, David Malamud, John Norton, and Jim Weatherall, to name just a few. Just by way of sort of contextualizing this view, the new received view is the basis, I think, for a number of further theses within general philosophy of science. So this example, this case of Newtonian gravitation has been used to make a number of assertions within general philosophy of science. One is the claim that the general relativity and Newtonian gravitation provide a template for implementing a completely general and mathematically precise approach to theory reduction. So Sam Fletcher uses the example to advance that sort of claim. It's been used, the Newtonian gravitation general relativity relationship, as understood on the new received view, has been argued to provide a paradigmatic case for analyzing the notion of approximate truth that a predecessor theory might bear to its successors. Jeff Barrett has argued for that. And Yuval Harari has argued that the transition from Newtonian gravitation understood along the lines of the new received view. The transition from Newtonian gravitation to general relativity provides concrete historical support for the thesis that theoretical progress in science cannot be equated with the accumulation of scientific knowledge. So I'm not going to elaborate much on these theses. This is just a way of illustrating how this new view has been invoked and used in other parts of the philosophies. So my aim in this talk is to, I hate this view. I want to argue against the new received view. I find it heretical and newfangled and deplorable. And in particular, I want to argue that the distinction between inertial structure and gravitational field is important and an important and substantive one within Newtonian gravitation. And the central way I'm going to make this argument is by claiming that the formalism actually used in advancing the gauge interpretation is a misconstrual and not a reformulation of Newtonian gravitation theory. Just by way of disclaimer, the aim is not to argue that Newtonian gravitation theory is free from all methodological and conceptual puzzles. Certainly don't think that. Let alone to argue that it is a superior theory to a curved space-time account of classical gravitational phenomena, what often goes by the label Newton-Cartan theory. But I do think that claims to the effect that Newtonian gravitation, as it is typically formulated, is in some sense a sort of non-perspicuous or misleading reformulation of Newton-Cartan theory, let alone that it is theoretically, it exhibits a sort of theoretically problematic gauge symmetry. Those claims strike me as mistaken, and that's what I'll be arguing against. Okay, so that's the sort of overview for the paper. In sections 2 and 3, I'm going to lay out what this symmetry argument is supposed to be and why I think the formulation used is extremely misleading. And then in sections 4 and 5, look at some of the ways that you might try to get out of the argument. Okay, so just a little bit of background. The idea behind this symmetry argument that the proponents of the new received view use is the idea that when we formulate Newtonian gravitation theory, there's a mathematical symmetry that undermines any sort of straightforward objective distinction between inertia and gravitation. And so the starting point for these sorts of arguments is this sort of Baroque mathematical structure that I put up on the left side. I'm not going to say too much about it, except that M is a manifold that is intended to represent space-time. The tensor field H is intended to give us a spatial metric that is defined on spatial slices of the space-time. T is a tensor field that's designed to give us a temporal metric. And then we have this all-important symbol, nabla, which encodes the affine structure of the space-time. We want it to be flat, and we want it to satisfy various other conditions. But what emerges from this is a sort of picture of space-time that looks like this, where we have space-time that can be foliated into simultaneity slices, and we have a notion of temporal distance from events on different simultaneity slices. And we have a spatial metric that allows us to define distances defined on the same simultaneity slices. And we have a notion of inertial structure, which is represented by the straight lines. Right? So this picture is what emerges from this characterization of that mathematical characterization of space. Okay, so that's the starting point for this sort of argument and this formulation of Newtonian gravitation. Particles are just going to be represented by time-like trajectories, so trajectories that move through the different spatial slices and are never tangent to a given simultaneity slice. Okay, so that's the space-time background for setting up the formulation. Then, of course, you have to provide the dynamics, and the dynamics connects the inertial structure with the gravitational field through Poisson's equation. Right? So we have phi on one side of the equation, which represents the gravitational potential, and rho, which represents the matter distribution. And the thought is that any theory of Newtonian gravitation should satisfy Poisson's equation. And then any time-like curve that represents the trajectory of a test particle is going to be one whose acceleration, that's what that elaborate gadget represents, is just given by the field generated by the potential. Right? So we start with a space-time, we add some matter to it, we make it satisfy Poisson's equation, it generates a gravitational potential, and then test objects are going to accelerate in accordance with the field generated by that gravitational potential. So that's the sort of picture that we're talking about. Right? That's the matter, and you have objects. You have a trajectory that's deviating from inertial motion in virtue of the gravitational field.
Just one question.
Yeah.
What's the normalization condition for your velocity?
The norm, they are, the normalized by proper time.
Oh, by time, so they can have as large as a component in space like that.
Yes. Yeah. Okay. So let's call this the Poisson formulation of Newtonian gravitation, and let's call the structure consisting of the space-time with the inertial structure and a potential and a matter distribution that satisfy Poisson's equation. Let's call any structure that satisfies these conditions a P model, right? So a model of the Poisson formulation. So on the surface, it's not obvious that one would claim that the distinction between inertial structure and gravitational field is gauged or conventional or arbitrary, because of course we're using the inertial structure and the potential in defining what the dynamics look like. Knox and others are going to claim that this way of understanding it is mistaken. And they do that by asking us to consider a pair of transformations. So a pair of transformations that takes an inertial structure and a gravitational potential into a new inertial structure and a new gravitational potential, right? And those are generated by taking some function whose spatial Laplacian is 0 and adding it to the existing potential and changing the Christoffel symbols associated with the inertial structure in this precise way. Remember that the temporal metric is the same across all of the spatial models. So the idea is find some function psi whose spatial Laplacian is 0 and use that to define transformation from a pair of inertial a pair consisting of an inertial structure and a gravitational field to generate a new one, a new pair. That's the idea. And so here's a sort of a visual way of understanding what this transformation looks like. Here we have some inertial structure, and we have some gravitational field. And what one is in effect doing in this transformation is augmenting the gravitational field and changing the inertial structure. And I'll come back to these two descriptions in a moment. But if all the math that just came on the previous slide looks unintelligible, just think of it as implementing this transition, right? Where the grid represents the inertial structure, and here we have the gravitational field. Okay, so the argument turns on this really remarkable mathematical theorem that Andre Troutman proved in the 60s, that transformation that I just defined constitutes a symmetry of the Poisson formulation. What does that mean? That means if you take two models, that satisfy the Poisson equation and are related by that transformation, they will be such that all test particles follow identical space-time trajectories in each model. So one way of seeing why that is, and these are just the same two diagrams again, but now I've drawn in an inertial trajectory. One way of seeing why that is just by noticing that effectively what this transformation does is increase the gravitational field, but change the standard by which you measure acceleration, right? So you have a greater, in affecting this transformation, you have a greater gravitational field, so you have more acceleration, but of course the curves that count as inertial or unaccelerated curves after the transformation are different. And so it gives rise to the same trajectories. That's the idea. So the argument is then supposed to be that what the symmetry reveals is that nothing in the theory fixes any one way of distinguishing space-time inertial structure from gravitational dynamical effects. So we're free to draw the split in whatever conventional way we choose. So that's how you get from it looking like there's a genuine objective distinction between inertial structure and gravitational structure to the idea that that split is entirely arbitrary and conventional. So this is Knox writing again in that same paper. The freedom in the choice of a flat connection is accompanied by a corresponding freedom in the definition of the gravitational field. These transformations include trivial transformations of the gravitational gauge potential, but also transformations of the gravitational field itself. The above considerations reveal that while the gravitational field and inertial frames are each subject to a gauge freedom, our choice of gauge for the two is not independent. Okay, So let's back up for a moment. Here's what we might, if I ask you to formulate Newtonian gravitation theory, this is the sort of thing you might start with, right? You might start by looking up the gravitational force, Newton's law of universal gravitation, which I listed here in integral form. And if you think of the gravitational force exerted on a body with mass m, and matter distribution is being given by this integral, then you can associate a particular gravitational field by that distribution rho that generates these gravitational forces on individual masses. So this is the sort of formulation that one would be led to before one learns about the Poisson equation. And I want to call this formulation the force formulation. Right? And so models that satisfy the fixed space-time structure that have already laid out, but are not framed in terms of the Poisson equation, but instead are framed in terms of a gravitational field that accelerates bodies given by this equation. I want to call those models F models, right? F for force. Okay. Now, the gauge argument makes essential use of the Poisson formulation. And so it's important that the Poisson formulation be a reformulation of the force formulation. And most textbooks will tell you that that's exactly what it is. But I think there are actually several reasons to think that the formulations are not equivalent. Right? And so that's sort of what I want to lay out. And I'll come back in passing as to why textbooks say they're equivalent. Okay, so there are sort of two examples, I think, that illustrate that these formulations are going to come apart, right? So the first one I'm calling sourceless interactions. So the idea is, consider a Newtonian universe consisting of a single particle, right? There's no other matter in this universe, and so there's no source of gravitational interactions to accelerate the particle, and so whatever the particle is doing, if it's sitting there or not, it should be engaged in inertial motion. Of course, if we're working in a Newtonian spacetime, then there is no distinction between just sitting there and regular inertial motion. And that's exactly what the force formulation says, right? There is no gravitational field because there's no matter in the universe. So there's no acceleration. That is not what the Poisson formulation says. Although there are going to be plenty of P models on which the particle does move inertially, there are also going to be models in which the particle is accelerating on account of what we would otherwise call a gravitational field. So here's the example, right? In this universe, we have a three-dimensional Poisson equation, which reduces because there's no matter to the Laplace equation. And there are plenty of solutions to the Laplace equation for which the gravitational field, right, del phi, is non-zero, right? One of them is just phi equals x, right? When that's the potential, the particle accelerates off in the minus x direction, right? And in fact, we can construct P models where the single particle is going off in any old direction we choose, just by picking A, B, and C in this expression for phi any way we like. Right? And so something has clearly gone wrong, right? This dynamics is not countenanced by the force formulation. So how could the Poisson formulation be a reformulation of it? That's the first thing. The second example is an example I'm calling gravitational repulsion. And the idea is this mismatch between what counts as a P model and what counts as an F model only gets magnified when we move to an explicitly four-dimensional context. So here the thought is, imagine that we have a universe in which matter is localized in some sort of spatial region, say it's all on that side of the room, and consider a test particle in motion outside that region, say on the other side of the room. Right? Now, that particle might be doing all sorts of different things, depending on its dynamical state. But there's one thing it can't be doing. Right? One thing it can't be doing is accelerating away from the matter region. Right? And it certainly can't have an acceleration away from the matter region that is increasing or varying indeterministically. Right? But there are plenty of P models for which exactly those things are happening. Okay. So suppose rho is the matter distribution for the matter in the universe. The Poisson equation is linear, right? So if we have a solution, then so is any other solution where what we add to it is a harmonic function. That is a solution to Laplace's equation. And amongst those solutions, there will be plenty of scalar functions. Amongst the harmonic functions, there will be plenty of scalar functions that are uniformly increasing across any simultaneity slice, but whose rate of uniform increase is itself increasing or varying indeterministically from one simultaneity slice to the next. All right, any phi like that, any psi like that, it can be added, and we're still going to have a solution to the Poisson equations, and so we're still going to have a P model, right? And what psi is doing is it's adding a uniform background field that varies with time. And if we make that background field sufficiently steep, it's going to, as it were, produce a gravitational force on our particle that's greater than the force of all the matter in the universe, right? And it's thereby going to cause. It's just right now.
But when you boost, yeah.
And it's thereby going to cause the particle to accelerate at an increasing or indeterministic rate in the direction away from all matter, right? So given any sort of given matter that's localized in space and something away from it, we'll always be able to find another P model that takes that introduces a background field that causes the particle to accelerate away from all matter, and in fact, we'll do so if we want at a varying and indeterministic rate. And it's hard to see how any formulation that encounters such situations as models could be a reformulation of Newtonian gravitation. Okay, so of course, in this sort of situation, the distance between the test particle and the matter region doesn't change, because of course that background field that we're adding accelerates all of the matter equally, including all the matter in the universe. But I think to object on this ground is to sort of miss the point. Because the Poisson formulation was originally proposed as an alternative way of encoding the dynamical picture associated with the force formulation. And within the force formulation, there's clearly a theoretical difference between the force dynamics, between systems of bodies moving inertially and systems of bodies that are accelerating. And it's a clear consequence of the force formulation that a test particle can't have its acceleration directed away from all matter, whatever that matter might be doing. There are no F models containing such a trajectory. But there are P models. And so the Poisson formulation is incapable of being understood as reformulating the dynamical picture associated with the force formulation. And I think that that's true whenever one ends up deciding about how the Poisson formulation is best understood. Okay. Now, what if we impose boundary conditions? What do I mean by that? In both of the examples I give, the potential is unbounded at spatial infinity in at least one direction, one dimension. And if we require that it go to zero asymptotically as we move off to infinity, these inconvenient dynamical effects that are generated from the two examples vanish. And it looks again like we have a good reformulation of the force dynamics. What does this mean physically? Well, imposing this constraint amounts to the requirement that all dynamical influences on matter have their origins in other matter, for the boundary condition implies that test particles approach inertial motion as they get further and further from matter. So as you go off to infinity and the potential goes to zero, the field goes to zero, and you start moving inertially. Right? If you don't require that the potential go to zero, then of course the field need not drop off as you go to infinity. And so this seems like an entirely reasonable condition if our aim is a reformulation of Newtonian gravitation theory, right? Which after all is a theory about the dynamics of matter-matter interactions. And of course, this is exactly what the textbooks do when they tell you that the Poisson equation is a reformulation of Newtonian gravitation theory. So you might think, okay, well, why don't we just do this, right? But there's a cost to this move, and that cost is that by imposing these boundary conditions, you lose the symmetry between inertia and gravitation. So recall that this is the transformation. Right? So this pair of transformations is a transformation that generated the gauge symmetry argument. But if we require that potentials go to 0 and infinity, then the only solution to Laplace's equation that satisfies that condition is going to be the 0 function. And so our transformation on the affine structure and on the potential are just going to become the identity transformations. So if we impose boundary conditions, then the symmetry vanishes, and the mapping that's defined by that pair of equations ends up just being the identity. I think in hindsight, we can see why the universal gravitation symmetry is problematic in the absence of boundary conditions, and that is that this transformation changes the very structure of the dynamics, right? It amounts to adding sourceless dynamical interactions and then covering up their observational effects by modifying the inertial structure. But once the dynamical structure is changed, right, then it's no longer a theory of matter-matter interactions, and there's no reason the resulting models have anything to do with Newtonian gravitation. This is something maybe we can come back to. There are still problems associated with Newtonian gravitation having to do with local observations revealing what the true inertial gravitation split is. But I consider those to be sort of epistemological and methodological defects of Newtonian gravitation, not defects that justify interpreting it in a way that is not a theory of matter-matter interactions. Okay.
Fine.
I'm doing fine.
You're like 8 minutes.
Oh, okay, perfect. Okay, so there's another sort of response someone might give to this argument. And that is to say, look, I'm really taking this too seriously, right? The Poisson formulation was never intended to be a reformulation, a strict reformulation of Newtonian gravitation theory. It was always intended to be a generalization of the force formulation, right? And so it's no surprise that there's going to be some disagreement between what counts as a P model and what counts as an F model for certain mass distributions. And in particular, for spatially infinite cosmologies in which the matter distribution is strictly positive and constant on a time slice, right? So a universe in which on any given simultaneity slice, matter is uniformly distributed throughout that slice, the gravitational field integral doesn't converge, right? So this integral, because this never drops off, right? The matter distribution never drops off. The integral just blows up, right? When you integrate over all of space. So for spatially infinite cosmologies, we find that the field isn't defined, right? The gravitational field is defined this way, right? And the integral formulation isn't defined. And so there are going to be no F models associated with such cosmologies, right? And lots of people take this to be problematic because, among other things, we take our universe, at least on a coarse grain scale, to be just such a universe. But there are plenty of P models that can accommodate such cosmologies. Canonical solution of Poisson's equation for a matter distribution like this is this sort of gravitational potential where Rho just functions as some arbitrary spatial location. In such a P model, right, the relative motion of all matter is to accelerate towards other matter. But the only matter that is actually not accelerating, that's truly moving inertially, is the matter at Rho. So here's an example. Here's a diagram that I've stolen from John Norton that illustrates how this works. The idea is that the matter at Rho actually moves inertially, but all the other matter is accelerated. But if you look at the relative motion, the relative accelerations between all the pieces of matter, they're all coalescing. Okay? So this is a solution, right? This is a matter, a dynamics that involving a homogeneous isotropic matter distribution that satisfies the Poisson equation.
But it has some strange feature, right?
Okay, I can do that. Okay, it does have some strange features. Before I go on, I just want to flag that for reasons that I guess we'll come back to in Q&A, John Norton, right, I don't mean to think that he endorses this solution. I've taken the diagram from him, but he denies these results. I mean, he's not happy with this sort of solution. Okay, so you might be inclined to think of the Poisson formulation as a generalization of the force formulation on account of its inability to deal with cosmological scenarios that intuitively also fall within the domain of Newtonian gravitation. And this, I think, this view is endorsed by David Malamud in 1995. He writes, consider first the relation of the force formulation to the Poisson formulation. Here, as I have indicated, I think there is a clear sense in which the latter is a generalization of the former, so the two are certainly not equivalent. But I should think that a proper appreciation of the relation between the theories would help to relieve, rather than intensify, any concerns one might have about the adequacy of the force formulation. The integral formulation, the force formulation, is not applicable to cosmological contexts of the sort we have considered. It seems natural to ask whether that limitation is in some sense essential, or whether instead it is possible to recast the theory so that it is applicable. Surely it counts in favor of the theory that the reformulation is not only possible, but relatively simple and straightforward. So I think Malamud is much too cavalier about the sense in which the Poisson formulation is a relatively simple and straightforward reformulation. Malamud's reasoning seems to be that because the Poisson equation with boundary conditions is generally thought to be strictly equivalent to the force formulation, dropping the constraints is sufficient to label the resulting formalism a clear generalization. But as we've seen, as I've tried to illustrate in this talk, dropping the boundary conditions has a profound impact on how the theory is interpreted. In particular, the two examples that I've developed both illustrate how the formalism can no longer be understood as an account of interactions between matter, right? And in addition, dropping the boundary conditions introduces a rampant indeterminism into the theory. Both features, I think, are arguably anathema to how we think about Newtonian gravitation theory, whether interpreted as positing a fundamental gravitational field or not. I think a better, more faithful generalization is one that imposes boundary conditions on the gravitational potential for a spatially finite realm, but which relaxes that constraint for cosmological situations of the sort described above. I think there's a good physical motivation for thinking of this as the appropriate generalization, namely it's grounded in the idea that this is a theory of matter-matter interactions. I think such a generalization provides a way of assimilating cosmological scenarios into Newtonian gravitation, but doesn't, against the new received view, involve abandoning an objective distinction between inertial structure and gravitational field. Okay.
Honestly, on time.
So I certainly agree with everything you were arguing. I'm just wondering, you know, of course, a lot of this turns on people saying this is a reformulation, and then maybe a reformulation with some cognitive advantage that some things are more obvious or something. But a reformulation means you've just got the same theory. And it seems that there's another point one could make here, and I'm just wondering what you think about it, which is what also happens to get you to general relativity. You know, you start with the observation that even in the Newtonian theory, if there were a perfectly constant gravitational field, not hard to get that, but okay, forget about where it comes from. Everything's now accelerating down at the same rate. All the relative motions remain the same. So this is the, you know, the elevator in free fall, blah, blah, blah. The relative motions of the particles remain the same. But then Einstein, takes an extra step. And that extra step is very important because, as you say, if you think of Newtonian gravity as a theory of matter and matter gravitational interactions, and you say, okay, but what about stuff that isn't matter? Maybe light for Newton. I mean, maybe it's a particle, maybe it's not. Maybe it's some kind of wavelength. Maybe there are particles that have zero gravitational mass or don't couple with the gravitational field or whatever. I mean, those are all theoretically open possibilities. And those will come out quite differently on these two formulations, right? Because if you reformulate the space-time structure itself, that should have an effect on everything in space-time, right? So you sort of ask Newton, look, should gravity affect light? Should there be gravitational bending of light? He might shrug and say, I'm not sure. I don't know what light is well enough to answer that question. But as soon as you go to GR, you say, sure, there better be, because light, whatever it is, it's propagating in space-time, and I've changed the space-time geometry. So this is just another way of saying that the rhetoric of these being reformulations, trying to geometrize away the force. It may be a better theory, it may be a prettier theory, but it sure looks like a different theory, right?
Yeah, I mean, I think it is a better theory.
The better theory than.
Sorry, I think the geometrized formulations of Newtonian gravitation, I think, have various sorts of like theoretical virtues.
But comparing with what?
Comparing it with Newtonian gravitation, just the older view.
Not that.
No, no. I mean, yeah, it's Newtonian gravitation much better than they are. Yeah, so I do think that the curved space-time formulation has various advantages. I mean, part of the reason I put up one of the initial slides showing how people have used this example is that people really want to read this as a reformulation back into the history of science, right? And use that claim as a way of extracting principles about the development of science, right? And so it's more than just a sort of like terminological question about what, are we going to call this a reformulation? What is really turning on this? It turns out that a lot of these other philosophical theses are turning precisely on whether or not we count this as a reformulation. Yeah.
Points. One is regarding this method that we show us without imposing boundary conditions, we basically don't have a unique solution. And I think in the cosmological setting, you face the same problem, right? Unless you tell me that exactly I have to have this particular follow-up, which is basically almost akin as giving me the solution without looking at the question, because so
good.
So I think it's in the flat case, in the localized case, you can have this, say, natural requirement of requiring things go to zero. But in the cosmological case, you don't have any alternative. And my second point is the issue of if you bring in more forces, because here everything is gravitational. And if you bring in more forces, you would have to put an M playing a role in the motion, right? You will have your acceleration equation will have to have an M because the gravitational force is proportional to M.
Yes.
And then you would have to ask yourself the question, why is that M that appears there equal to the M that appears in the coupling with the gravitational field?
Okay, let me just the first question before I forget what I'm going to say about it.
Yeah.
So let me make that problem even worse, right? Right. So in this expression for the potential, R0 is entirely arbitrary, right? And so it can be any point in the universe, right? And so if you have a uniform rho distribution, there are an infinite number of solutions. There are an infinite number of solutions each of which correspond to a different R0, right? And you don't notice this, that this was sort of actually Norton's point in drawing this diagram. His point was that you don't actually notice this observationally because the relative acceleration speed in all the matter remains the same no matter which R0 you pick. But you have an infinite number of these different solutions, right? And he's really unhappy with that. And so what he wants to say is that that in the cosmological scenario, acceleration is relative in Newtonian gravitation theory, right? I am very unhappy with that sort of answer because it's sort of like it seems analogous to me to saying something like, well, I don't think the scalar and vector potentials are real except when solenoids are present. It sort of amounts to interpreting certain models, interpreting the ontology of certain models in the theory very different than the way you interpret the ontology of all the other models in the theory. Right? So I don't like Norton's own solution to it. You might have noticed in the abstract of this talk, it said that I was going to argue that Newtonian cosmology is inconsistent, but now I've sort of ended up offering a generalization on which there is no sort of contradiction. And part of the reason for that is that I started to have doubts about exactly how bad a problem this is. Right? So one thing to note, I'll just make a couple comments, right, about whether or not this is a sort of result that we should be willing to live with. Right? One thing to note, and let me see if I can find the equation. One thing to note is that one thing that people point out is that in a uniform matter distribution, you might expect the gravitational field to be uniform, right? But it's mathematically impossible to satisfy the Poisson equation if with as long as rho isn't 0 with a uniform gravitational field. So as long as you're sticking to, as long as you're requiring the Poisson equation hold, there's no way that you're going to be able to generate a uniform gravitational field. Right? Now, how bad is this? I guess ultimately, I think that funny things can happen in infinity. Right? And part of me wonders whether or not
it's not only at infinity, they will affect everything.
Well, sure. No, so sorry, but not at infinity. What I mean is, funny things are going to happen in
All over.
But in the case where matter is infinitely homogeneous, right? So we know, of course, that electrostatics completely breaks down. Right? There are no models where charge is uniform and homogeneous for the same reason. It has the same mathematical structure as the force formulation. So I think that this is I think an oddity of an infinite cosmological matter distribution, right? But I don't think there's any inconsistency in that. What it means is that there are going to be a lot of empirically equivalent models, some one of which is going to be the correct one. But I'm unconvinced that that is as problematic as people make it out to be.
I think without boundary conditions, you simply don't know what is the equation.
You know what the solutions there
You
are.
don't know what is the solution.
You do know there are an infinite number of solutions.
But not only infinite in the way you wrote, there are many more infinite. There are many solutions that don't fit into your scheme. For instance, take ax squared plus by squared plus c z squared, and take c equals minus I minus b, equal to minus I minus b. That is a solution of this for every a and b. So this is an infinity that doesn't fit into that category.
Yeah, I'm gonna have to think about that. That's the issue. That is not the problem that generally comes up when people talk about the puzzles in
I'm just thinking of,
No, this is good, I appreciate it. Yeah, so maybe, I mean, one option. Right, so what I wanted to do is restrict, as a generalization, I want to restrict the boundary conditions, except in the case where, except in the case where we have these homogeneous infinite matter distributions. Maybe an additional condition needs to be added to that to rule out the matter-matter interactions. I would have to look. I'll get the specific solution from you afterwards. Yeah, thanks.
Or just have an extra long break and talk to the speaker policy. That's great. Let's thank Kevin again.